Now that we've had quite a bit of practice of first derivative test and second derivative test, finding critical points and inflection points, we're going to be putting all of the information that we can about a graph about a function together in order to produce an accurate, detailed graph. The information that we normally seek are things like the domain, the intercepts, all potential asymptotes, local maximum, local minimum, intervals of increase, decrease, inflection points, and intervals of concavity. So let's take a look at the function that came through an application of crows and whelks. If you remember, crows fly up to drop a whelk onto a rock beach in the hopes to break the shell and have dinner or lunch. So the function that we were working with is this one, and that describes the average number of drops required in order to break the whelk from the height h, where h is bigger than 0.84. We would like to sketch this graph. So we're going to go through all of these steps, collect all the possible information about the graph, and then put it all together. Let's talk about the domain of my function. So domain are all the possible x values that I can plug into the function. In this case, our x is called h. So oftentimes in terms of domain, it's better to think about what is there that I cannot plug in. And it becomes very clear very quickly that I cannot plug in h equals 0.84 because that's what's going to make denominator equal to 0. Every other number I can plug in with no problem. So my domain is everything except for h being 0.84. The next on our list are vertical asymptotes and horizontal asymptotes. Let's start with vertical asymptotes. Remembering when we talked about them a couple of weeks ago, vertical asymptotes are the values near which the function approaches infinity. In terms of functions that are rational, vertical asymptotes will occur when the denominator is 0. So in this case, my vertical asymptote is exactly the value that's not in the domain, h being 0.84. What about horizontal asymptotes? For horizontal asymptotes, you're going to have to do a little bit more work because we're going to have to compute the limit of our function as h goes to infinity. So the limit of 1 plus 20.4 all over h minus 0.84. Okay, remembering how to compute limits, there's a couple of ways to compute this one. But essentially when h is going to infinity, this is a number 20 divided by infinity. So this whole portion is going to go to 0, which means the entire limit goes to 1. So I do have a horizontal asymptote and it occurs at 1. Great. Then I'm going to look for intercepts of x-intercepts and y-intercepts. And I'm going to leave this to you to actually work out, but my intercepts should work out to be x is minus 19.56 and y is minus 23.3. Let's move into the critical points, intervals of increase, decrease, and potential inflection points. So for critical points, remember that the first thing I have to do is find the derivative, set it to be 0 or not exist. In this case, the derivative is provided to me, so I just have to consider two cases. When is the derivative 0 and when does it not exist? With rational functions, this actually becomes a fairly straightforward process. If I give you a fraction, when is the fraction ever 0? The fraction is only 0 when the top is 0. So in this case, this will correspond to top being 0. Now the top here is minus 20.4. That's never 0, which means that this produces no solutions. Okay? Now the derivative does not exist. When does the fraction not exist? A fraction does not exist exactly when the bottom is 0. So I have these two cases that I will always follow, and the bottom in this case is 0 when h is equal to 0.84. So that is going to be one of my critical points, and in fact, this is then my only critical point under consideration. Okay, so I'm going to construct myself, a number line. Just like we have been, I'm going to put all my critical points on it. Now I only have 1.84, and I'm going to analyze the behavior of the function before and after. So I'm interested in the sign of the derivative before and after this point. Okay, so I'm going to pick a number here, let's say 0, and I'm going to plug it into my derivative to figure out if it's positive or negative. You can go through with a calculator, you'll notice that it's negative. I'm going to pick a number after 0.84, plug it into the derivative. You notice that the derivative, in fact, is always going to be negative because no matter what I plug in here, this gets squared and then it turns into negative. Anything squared is positive, so that negative sign in the front guarantees that the derivative will always be negative, which means that my function was decreasing and is decreasing afterwards. So it's not, in fact, a local minimum or local maximum. That's not a big surprise because this 0.84 was a vertical asymptote in the first place. So this is another type of information that is really useful to include on this analysis of the first and second derivative. Now I'm going to do an analogous type of analysis, but on a second derivative in order to discover potential inflection points, and intervals of concavity. Okay, so I'm just going to get a new slide so I don't have to squish everything in here. For the potential inflection points, I'm going to look for when the second derivative is equal to 0 and when the second derivative does not exist. Okay, those are going to be my two main cases here. Now, as before, not only am I given a second derivative, it is once again a really nice one because it's just one fraction. A fraction is only 0 when the top is 0, and a fraction does not exist when the bottom is 0. I would like to warn you here, though, that this type of top-bottom analysis only works if your function is one big fraction. So, for example, it wouldn't work on this part here because you don't have one fraction. You have 1 plus something else. So you cannot say that this whole thing is 0 when the top of a fraction is 0. This analysis only works if your function is just one compact fraction all in one. Okay? So the top is 0. Well, the top in this case is 40.8. That's never 0, so this produces no solutions. And the bottom is 0, once again, at the value of 0.84. Okay, so in this case, this is my only potential inflection point. And I'm going to draw, once again, a number line and put all of my newly found potential inflection points on it. Having learned from last time that asymptotes are a good thing to note here, I'm going to note that this is actually a vertical asymptote. This immediately tells me that this cannot be an inflection point because there is no physical point there. However, concavity might actually still change around the asymptote. So let's go through the analysis just to see that. So again, I'm going to analyze the behavior of the second, or the sign of the second derivative that will tell me the behavior of the function. I'm going to pick a number here and plug it into the second derivative. If I pick, let's say 0, plug into the second derivative, I notice that it's going to be negative. And then I'm going to pick a number on this side of 0.84 and plug into the second derivative to discover that on this side, the second derivative is in fact positive. So my function was concave down before and becomes concave up after the asymptote. Now, equipped with all of this information about my function, I'm now going to put all of this together on one graph. All right, so I've just copied over all of the information, so I have it right in front of me, and let's start putting everything onto the graph that we've discovered. So first, I know that my vertical asymptote is at 0.84, so let's say this is my 0.84, and I have a vertical asymptote here. Remember that vertical asymptotes actually cannot get crossed, so this already immediately divides my region sort of into two pieces. I also know that this function has a horizontal asymptote at 1. So I'm going to put my horizontal asymptote here at 1. Remember that horizontal asymptotes can get crossed as long as they eventually get approached by the function. Okay, and then in the process of analysis, I've also discovered that I actually do have axes intercept. X and Y intercepts are large negative numbers, so I'm just going to create this kind of squishy axis here and mark this to be -20 here and this to be let's say minus 23.3 there. So my graph goes through the point somewhere near minus 20. So let's say here and at negative 23.3. Now, notice that my function on all of the numbers is always decreasing. So somehow now I have to put function pieces onto this graph, and I know there will be pieces because of the vertical asymptote, so I'm going to have an infinite jump there. But no matter what I draw must be decreasing always. And before my vertical asymptote here, it's decreasing in a concave down manner, and after it's decreasing in the concave up manner. Just this alone creates enough restrictions that there's essentially only one way the function can go. And I strongly encourage you to pause the video right now and try to fit the pieces of the function together yourself before you see me do this. Okay, so pause right now and we'll be back in a second. Okay, so what you really should have is some kind of graph that looks like, that looks like this. Decreasing and concave down, approaching the vertical asymptote, and then on the graph here, decreasing, approaching the vertical asymptote here, and a horizontal asymptote there. Let's take a look at another example of sketching. We're going to start with a simple looking polynomial. It's a cubic. First of all, because it's a polynomial, we can actually use power analysis to produce a fairly rough sketch of this function. So as the very first step, this is what we can think about. According to the power analysis here, the highest powers will dominate for large values of x, which means that for large x, the function f of x looks approximately like x cubed, and for small values of x, or near the origin, the function will look approximately like minus 45x, its smallest power. So that means if I am to produce a very little sketch of a graph just for the near origin and end behavior, for near the origin, minus 45x is going to be a linear behavior with the negative slope, so look like this. And for large values of x, it's going to look like x cubed. So that means that I'm going to take the end pieces of my snaky shape of the x cubed function. So connecting these two in the most natural way, I can see that the graph is going to be something like this. Now, the dominating power analysis, of course, tells me nothing of the intercepts and the highs and lows of the function, of where it turns and whatnot, but it produces an expectation in just a few seconds of what is the shape of the graph that we are expecting to see. Now, going through our big sketching process, we will go through all of the elements. First of all, we're going to talk about the domain. Given that this is a polynomial, there's no denominators, no issues. The domain is all real numbers. So we're also then looking at no asymptotes here, no holes, no infinite jumps, nothing like that. Next up on our list, we had intercepts. The intercepts that are easy to find are always the y-intercept, because for that, we will set x to be 0 and simply compute. If I set x to be 0 everywhere here, I will get that y is also equal to 0, which means that the y-intercept here is at the origin. For the x-intercept, we need to set y to be 0, which means that we're now having to solve the cubic equation x cubed minus 3x squared minus 45x is equal to 0. Now, it's a cubic equation, we don't have a cubic formula, but one thing that we can notice is there is an x in every single term, which means that I can actually take it out. And what am I going to have? X squared minus 3x minus 45 equals to 0. So this will produce x equals 0 as one of the roots, because again, remember, the product of two things being equal to 0 means that either the first thing is 0 or the second thing is 0. Now, setting the second thing is 0, we can see that what we have for ourselves here is a quadratic equation. And quadratic equations, of course, we certainly know how to solve. You can try to find the two factors here, but in this case, you actually have to use the quadratic formula because the roots are not very beautiful and very carefully constructed integers. So the roots in this case are going to be 3 plus or minus square root of 21 divided by 2. And so this is actually, let's say, approximately, because we would like to sketch them, minus 5.4 and 8.4. Okay, and this is given to us via quadratic formula. So not something that we're going to be able to just find out using the nice integers being factored out into the quadratic form. So, but this is an important lesson, and this is why this example is constructed like that, is just because you can't factor this into two beautiful factors doesn't mean that the quadratic cannot be solved. You always have quadratic formula that you can rely on to solve any quadratic equation that you're given. Okay, we're done with the intercepts. Next up were the asymptotes. So we have to think about the vertical asymptotes, where the denominator of a rational function is 0. There is none. There's no denominator, so no vertical asymptote. And for horizontal asymptote, so I guess I can denote that vertical asymptote's none. For horizontal asymptote, I'm going to have to take the limit as x goes to infinity of my function. So x cubed minus 3x squared minus 45x. Here, though, I know that for large values of x, this entire polynomial will look like its biggest power, so x cubed. And thinking of what is the limit of x cubed as x approaches infinity, I will of course get infinity. So that means there are no horizontal asymptotes either, because we did not end up with a number to approach near the infinity. Next up in our analysis were the critical points. Now, in order for us to think about critical points, we first of all have to find what the derivative of the function is. So here, the derivative is going to be 3x squared minus 6x minus 45. And remember that for critical points, we need to set the derivative to be 0 and then to find out where it does not exist. So setting the derivative to be 0, we will end up with a quadratic equation being set to 0, and this one we can actually solve. This one will have very nice clean roots. So the roots in this case are going to be minus 3 and 5. Notice that I'm skipping some steps in the algebra here because I trust that at this point you are going to be able to actually perform the simple algebraic steps. What I'm interested in is putting all of this information back together and producing an actual sketch of the function. Now, for the derivative not existing, the derivative here is a polynomial, which means that the domain of it is all real numbers. So this will produce no solutions whatsoever. Now that I have my first derivative and the critical points, I will construct a number line to analyze the behavior of the derivative and the function in the regions created by the critical points. So I'm putting the critical points on my real line, so minus 3 and 5. And I'm going to think about the sign of the derivative and what that means for the function itself in order to figure out whether any of these critical points correspond to local maximum or minimum. So, as before, that means that I can simply pick a number in any one of these three created regions, plug them into the derivative to figure out whether it's positive or negative. Again, remember, I don't actually care what number it is. All I care about is whether it's positive or negative. So, for example, I can pick minus 5, plug it into the derivative to figure out if it's positive or negative. I'm going to skip the calculations. This one is going to be positive. I can pick a number in this region here, so anything between negative 3 and 5 will do. Let's pick a 0 because it's easy to work with. Plug this into here. 0 minus 0 is 0. I end up with negative 45, which means that the derivative is going to be negative. And then finally, this last piece, I pick a number here, let's say 1,000,000. I plug 1,000,000 into here. I will see that the two terms with the x's will keep the entire thing positive, and so I will end up with a positive derivative here. So what does that mean for the function itself? If the derivative is positive, it means that the function is increasing. If the derivative is negative, it's decreasing. If the derivative is positive again, it's increasing. And now following in the trend of what the derivative gives me, the first derivative test says if it's increasing and then decreasing, it exists at the point, we have ourselves a local maximum. And on the other end, if we're decreasing first and then increasing, we are creating a valley with the point at the bottom being the critical point, meaning that we have a local minimum. So the behavior of the first derivative analyzed, we move on to the second derivative. So for the second derivative, we are thinking of the potential inflection points. The second derivative is then going to be, so remember our first derivative was 3x squared, so the derivative of that is 6x, minus 6x, so the derivative of that is minus 6, and then I had negative 45, the derivative of that is going to be 0. So for the potential inflection points, I am looking at the second derivative being 0 and the second derivative not existing. So where is it 0? 6x minus 6 is 0. This will give me x is equal to 1. And the second derivative not existing, well, this is still a polynomial, so this still produces no solutions. Okay, so I only have myself one potential inflection point, and I'm going to, once again, create a number line to analyze the behavior of the function around its potential inflection point. So the second derivative and the function itself. This divides my entire number line into two regions. I'm going to pick a number here and plug it into the second derivative. So for example, here's where 0 is. I plug it into my second derivative. The sign is going to be negative. I then pick a number on this side, let's say 10. I plug it into my second derivative. 60 minus 6 is a positive number, so this will be positive. That means if the second derivative is negative, the function itself is concave down. And when the second derivative is positive, the function is concave up. The concavity changes around 1, and 1 is an actual point on the function, which means that we actually have ourselves an inflection point at 1. Excellent. Now we have all the information we need to actually construct a graph of our function. The only other thing that we might want to think about is plugging in important points. So plug important points back into the function so that we actually have the coordinates for all of those points. So if we look back here, we know that our critical points are at negative 3 and 5, local max and local min, but we don't know how high those points are. Is the function looking like this, or is it looking more like this, right? I would like to know where to actually place these two different points. So I'm going to plug in negative 3 and 5 back into the function itself, and I'm also going to plug in my inflection point, 1, back into the function as well. So negative 3 and 5 and 1 all go into the function so that I can calculate the y-coordinate of each one of them. At negative 3, I'm going to get 81. And remember that this was my local maximum. At 5, I'm going to get minus 175. And remember from the previous slide, this was a local minimum. And when I plug in a 1, I'm going to get minus 47. And so here from this slide, we know that this is actually an inflection point. Now with all of this information on hand, I am going to start with the graph. Before you put on any kind of scale on your graph, actually take a look at what scale your points come in at. Notice here that while my x-coordinates are fairly small, my y-coordinates range drastically. So don't start with 1 on the y-axis here, because we certainly don't want to be counting down to minus 175, 1 unit at a time. Okay, so in terms of the x-coordinates, I know that I am looking at the range of negative 3 to 5 being where sort of the interesting points are. So this is something I can certainly go one at a time here. But for the y coordinates, I'm going to have to really shrink my scale. So minus 47, let's say, is going to be somewhere here. Maybe that's not even low enough because I need minus 175. So let's say this is minus 47. Let's say this is minus 175. And on the other side, I'm going to have 81 as my y-coordinate. Okay, now let's place the actual points on the graph. From the previous slide, I also know that the function actually intersects the x-axis at the origin. So there's one point here, negative 3 and 81. This is this point right here. And I'm actually going to label it on the graph immediately so that when I'm putting the picture of the graph in, I know that this is supposed to be a local mountain, a local hill, a local max. For the next point, I have 5 and negative 175, and this is going to be a local min. And finally, I have 1 and minus 47, so I better label this on the other side so that I can actually place the point here, and this is my inflection point. So now, putting all of this information together, let's take a look first at my first derivative analysis. I'm supposed to be increasing to local max and then decreasing and then increasing again. So that means I am increasing up to this point. I am then decreasing all the way to local minimum, and then I'm increasing forever afterwards. What the actual shape of the function, though, is given to me by the second derivative analysis. So notice that up until point 1, I need to be doing my increases and decreases in the concave down manner. Okay, keeping this in mind, I need to go up to the local max in the concave down manner, down through the origin, all the way to my inflection point, all in the concave down style. Afterwards, I know I still need to be decreasing to local max and increasing afterwards, but now I know I need to be doing this in a concave up way. So at the inflection point is where my concavity will change, and I will start concaving up all the way down. And I just realized too that I didn't actually put down 2 more important points on my graph, and those were my x-intercepts, right, that I calculated on the previous slide as this point being minus 5.4, so I'm not too far off on my scale, and this point was about 8.4, right? These were my x-intercepts on either side. Perfect. And here we have ourselves a pretty accurate graph of our function. Notice that this overall shape matches the shape that we discovered using the power analysis. It is linear with a negative slope near the origin, and it follows the cubic end behavior on both sides. But calculus tools allowed us to figure out the local maximum, minimums, inflection points, and the overall more precise shape of our function. Next up, let's take a look at the function that involves fractional or negative powers. In particular, this function that we've actually seen before, x minus 1 over x. If we are to sketch the graph of it, we still have to go through all of the steps. So first up is discussing the domain. Notice here, of course, we have a denominator, and that cannot be 0, so the domain is all real numbers except for 0. Next up, we can talk about intercepts, and as per usual, we can do the y-intercepts first because they're easier. However, in this case, it's a little bit trickier. So for y-intercepts, we will need to set x to be 0, but that is precisely the point not in the domain. So that's impossible, which means there are no y-intercepts. This graph never intersects the y-axis. The x-intercept means I need to set y to be 0. So x minus 1 over x has to be 0. And there's a couple of ways to proceed to actually solve this equation. You can do common denominators at this point, or you can bring the 1 over x over to the right-hand side and then cross-multiply. Either way, I will leave this up to you, but your answer should come out to be plus and minus 1. So 2 x-intercepts at positive 1 and at a negative 1. Next, we are discussing the asymptotes. For the vertical asymptotes, the denominator of some existing fraction within the function has to be 0 if it's a rational function. And here, of course, we do have a denominator, it's x, which is not in the domain, which already indicates the fact that we're probably expecting an asymptote. And indeed, x equals 0 is our vertical asymptote. For the horizontal asymptote, we have to calculate the limit as x goes to infinity of x minus 1 over x. Let's see what we have here. If I think about plugging infinity in, I will have infinity minus the limit of 1 over x, so essentially 0. This is obviously going to dominate, producing infinity as the answer, which means that there's no horizontal asymptotes, because this is not a number that a horizontal asymptote can be. Next up on our list are the critical points and potential inflection points. But this function is the one that we worked with before, where we actually discussed the critical and inflection points. So I will simply copy paste our analysis from before onto this slide. And with this information, we can produce the graph of our function. So again, I'm going to sketch the axes first and then think about what kind of scale do I want to put on them. Well, I know that for the x equals 0 or the y-axis, that's going to be an asymptote. So first of all, I can somehow indicate that. If I just go sort of close to it and maybe label this as the vertical asymptote, then this will remain clear. And then I know that at plus n minus 1, I have x-intercepts, and everything in our critical points and inflection points analysis rotates around 0. So I know that really my only points of interest here are plus and minus 1. So I'm going to move them a little bit away from the axis and not be terribly close to it so I can actually see the behavior near them. All right, so these are the points where the graph intersects the x-axis. So I know that those are the points on the graph. And then I simply have to follow the shapes suggested to me by the first and second derivative analysis. So the first derivative analysis says that the function is always increasing. So no matter what I do, on either side of the vertical asymptote, my function has to be increasing and somehow also go through these intercepts. The second derivative analysis says that on the left-hand side of 0, it is increasing, but it's increasing in the concave up manner, so it must increase this way. Whereas on the right-hand side of 0, it's still increasing, but it's increasing in the downward concavity manner. So something like this. With all of this in mind, I also have to remember that this is my vertical asymptote, and therefore I must actually approach it as I get closer and closer to it in the limit. So this is a pretty good shape for concave down increase, and now I just need a similar one for concave up increase on this side while approaching the vertical asymptote. Okay, not too bad. This is the graph of our function. Once again, you do have Desmos on hand. So take a look, graph the sketch of this function and take a look at how close our sketch is to the one produced by the actual computer software, a graphing calculator. One more example here. This is a standard type of example for these questions. I will give you the function, the first derivative, and the second derivative, so that you can perform the derivative analysis without having to actually derive the formulas yourselves. This curve is called a wedge of Agnesi. Agnesi was an Italian mathematician, Maria Gaetana Agnesi, and she published actually one of the first calculus books in 1748. Think about this. This is how old the rigorous study of calculus actually is. And one of the curves that she studied in the book are used as an example with this particular curve. Now, the name of it, the wedge of Agnesi, is actually a bit of a mistranslation. She called it a versiera, which meant a sailing shape or a turning shape, depending on the translation. But in the translation from Italian to English, something got lost a little bit. A couple of letters got permuted, which resulted in the word being the English word for wedge. So this is how the name wedge of Agnesi actually came to be, and now this is a fairly standard name to refer to the curve. This actual function appears in a bunch of applications within the probability and statistics, so it is a curve that has very interesting uses. Now, this is our function, and if we want to sketch it, we will once again have to go through all of the steps that we have seen before. We're going to talk about domain, we're going to talk about intercepts, we're going to talk about vertical and horizontal asymptotes, then we're going to figure out what the critical points are, what the potential inflection points are, and put everything together onto one graph. Because we've already seen all of these tools being used before, you should pause the video and try this out for yourself. Go through all the steps, figure out all of the information you need to have, and then try to put it all together onto one graph. Okay, so for the domain, we're taking a look at our function here, it has a denominator, but the denominator can never be 0, which means that the domain is going to be all real numbers. For the intercepts, for the y-intercept, we're going to set x to be 0. And what are we going to produce? If I set x to be 0, I get 1 over 1. The y-intercept is equal to 1. So we have 1 point on the graph that we can put there right away. For the x-intercept, we set y to be 0. And what are we going to get? We have 1 over x squared plus 1 has to equal to 0. And here's where we can employ our trick of a fraction is only ever 0 if the top of it is 0. But the top here is 1. 1 can never be 0. So this gives us no solutions. So this function never actually intersects the x-axis. For the vertical asymptotes, the function has a denominator. It's a rational function. So the vertical asymptotes will come from the denominator being equal to 0. But this expression can never be equal to 0. So for the vertical asymptotes, we have none. For the horizontal asymptotes, we need to take the limit as x goes to infinity of the function itself. And what do we have here? So if I plug in, hypothetically, infinity in for x, what am I going to get? I'm going to get 1 over a very, very large number. 1 over infinity is how I can write it out in concept, which means that I'm dividing a constant, a 1, by a very, very large number, producing a very, very small number indeed. So that means that I do have a horizontal asymptote, and my horizontal asymptote is x-axis. Okay, y equals 0. Next, I need to figure out what my critical points are. Now, for critical points, I need to know the derivative of the function. Luckily, the derivative is actually given to me right here. So for critical points, I need to figure out when the derivative is equal to 0 and when the derivative does not exist. When I have one compact fraction like this, it's equal to 0 only if the top of it is 0. So this helps me solve for when the derivative is 0, minus 2x is 0, which means that x is equal to 0. For the second case of the derivative not existing, the fraction, one compact, one cohesive fraction, only ever does not exist if the bottom of it is 0. Now the bottom of it has the exact same factor as before, which we know has no solutions for it being 0. So this particular case produces no solutions. And now I need to put all of this onto a number line so I can actually think about the behavior of the derivative and increase, decrease of the function. So my only critical point here is x equals 0, which means that it's going to be the only point that goes onto my real line here. And now I'm going to go through the behavior of the function, of the function's derivative, and of the function. Pick a number to the left of 0, plug it into the derivative, so plug it into here to figure out if it's positive or negative. It will be positive. Plug a number on the other side of 0 into the derivative, figure out if it's positive or negative, it's going to be negative. So that means that my function was increasing and then decreasing. At 0, I still have an actual point. In fact, at 0, I have a y-intercept, which means that I have a real point here. And so this is indeed a local maximum. Fantastic. This is good news. Now I just have to do the exact same analysis, but on the second derivative in order to figure out potential and real points of inflection. So for the potential inflection points, I need to set the second derivative to be 0 and to find out when it does not exist. And so here the analysis is going to be identical in a sense of the second derivative is also a compact fraction. So it's equal to 0 if the top is 0 and it does not exist if the bottom is 0. The bottom is 0 has the same factor, so this will still produce no solutions for us, but the top of it is going to be 0 when 6x squared minus 2 is 0. And if we solve this equation, this will give us two roots. And they're not nice rational numbers, they are rational. Plus and minus square root of 1/3. Again, I'm leaving some of the algebra here for you to do. Okay, and now I just need to once again produce my trusty little number line, put all of the potential inflection points on it. So here I have 2, negative root 1 over 3 and positive root 1 over 3. Let me just move this out here for now. Okay, and so that means that for the second derivative analysis, my number line is split into 3 pieces. So I'll plug in a point here, here, and here into, where is it? There we go, into the second derivative to figure out if it's positive or negative. So plugging that into second derivative will yield positive, negative, positive, which means it's concave up, down, and up. And again, because the domain is all real numbers, and so all of these numbers are actual points on the function, I have found myself an inflection point at negative 1/3 and an inflection point at a positive square root of 1/3. So now, taking all of this information all together, I am going to put it all together onto the same graph. Now remember that the last piece of usefulness, let's say, that came from this analysis before we started putting things on the graph is thinking about taking the important points and figuring out their y coordinates. So I'm going to skip calculations here and simply approximate on the graph, but I encourage you to actually plug the important points in to figure out how high on the graph they lie. So altogether, what do I have? I have that the graph intersects the y-axis at 1, this point right here. This also happens to be the point of local maximum. So I'm going to immediately label it so I don't forget that that's what it is. There are no vertical asymptotes, but x-axis is a horizontal asymptote. So I know that my graph will approach the x-axis into the infinity and into the negative infinity. However, I also know that it will never actually intersect it either. So this is one of the cases where the horizontal asymptote does not actually ever get crossed as well. And then according to my increase and concavity, I need to be increasing all the way up to 0. But up until negative root of 1/3, I need to be increasing in the concave up manner. And then afterwards, I'm going to be increasing in the concave down manner. So the other points that I want to have here are root 1 over 3 and negative root 1 over 3. So let's say you've computed the values and they will lie somewhere up here. I need to be increasing and concave up to this point. And then I need to change concavity into concave down, continue in the concave down manner until the positive root of 1/3, and then switch back to being concave up. So this is my inflection point here, and this is my inflection point here. This, ladies and gentlemen, is the witch of Agnesi curve. Now we've talked about how to find local maximum and minimum. What about global extrema? The extreme value theorem actually gives us a very easy way to do so. It says that if I start with a continuous function on a closed interval, so a specified interval, then I am guaranteed that my function will attain both global maximum and the global minimum on that interval, potentially at the endpoints. So if we just sketch ourselves an example of a function, doesn't matter what it looks like. Let's say I have a function that looks like this. Okay, what it's saying is if I pick a window that I look at the function through, I'm guaranteed to see the highest point and the lowest point. They might occur at the natural peaks and valleys, at the local maximum and minimum, or they might happen at the endpoints. So for example, if I take a look at this as my closed interval, so if my window is here, then my global maximum, so I'm only considering this piece of the function here, then my global maximum occurs not where it naturally has a peak, but rather at the endpoint here, because it happens to get cut off at the higher point than the natural peak would have produced. The global minimum, though, does occur at a naturally at a natural spot where the derivative in this case is 0, okay? But what this says is that if you're asked to find a global maximum or global minimum, all you have to check are critical points and endpoints of your interval. You don't have to perform any other kind of analysis.
So for our first problem here, let's take the function that we already work with, x minus 1 over x, and look for global extrema, first on the interval from 2 to 4, and then on the interval from 0 to 4. So, as already discussed, all we need to do is check the critical points and the endpoints. So let's make sure that we write down our procedure here. Now, we already know what the critical points of this function are because we have determined them before. For the critical points in general, we're going to have to take a derivative. Remember that the derivative of this was x squared plus 1 over x squared once we put it together into one cohesive fraction. And then, in order to determine the critical points, we must look at two different cases, when the derivative is 0 and when it doesn't exist. The derivative being 0 produced no solutions. The derivative not existing produced one solution, x being 0. So this is our only critical point. Endpoints for the first interval that we're looking at here are 2 and 4. So x equals 2 and x equals 4. Now notice that if we're asked for the global extrema on this interval, then the point x0 does not actually lie within this interval, which means that for the global extrema case on 2 to 4, we're not even going to include this point because it's simply not in the interval of consideration. But what we're going to do next is plug in all critical points and endpoints into the function and find the highest and the lowest into function itself. So this is one thing that everybody always seems to forget is for the global extrema, once you've determined your critical and your endpoints, you no longer need a derivative. You're plugging all of them straight into your function. Again, because 0 does not belong to this interval, we're not going to plug in the critical point. For us, in this particular case, it's actually outside of the domain of interest. So we're going to take a look at the function is called g. So we're going to take a look at g of 2, because that's one of our endpoints. And we're going to look at g of 4. So if I just plug in 2 into this function and I plug in 4 into this function, what are going to be my numbers? I have 1.5 for g of 2 and I have 3.75 for g of 4. This is it. These are the only 2 points that we're going to look at. We're going to look at the numbers. The highest number that we can see is the global max, and the lowest number that we can see is the global min. So in this case, this is my global min because it's the highest of the 2 numbers that I have, and this is my global max because it's the highest of the 2 numbers that I see. Now, this is what's going to happen on the interval between 2 and 4. What about the second part of this question? What about the interval from 0 to 4? So let's take a look what happens here. The situation does not change for critical points. I still have 0 as a critical point, except now it's actually in the interval. So for the critical points, x equals 0 will be considered. For the endpoints now, my endpoints of this interval are 0 and 4. So again, 0 and 4. So altogether, I have 3 points, but of course 2 of them are repeated. And so therefore, I'm actually only plugging in 2 points, 0 and 4. Unfortunately, while 0 is a critical and endpoint, it's not in the domain of the function because of course I cannot plug in 0. So if I am to figure out what happens at 0, instead of plugging it in, I will have to consider a limit near 0, okay? So I'm going to say plug in, but in quotation, x equals 0 and x equals 4, because I realize that plugging in 0 actually involves computing limit as x goes to 0 of my function. And for the second one, I am actually able to plug in 4. Now I already plugged in 4, so I know what the number is there, 3.75. But what about the limit? Well, if I plug in 0 here, it means that I'm plugging a very, very small number, which means that this becomes a very, very large number. 0 minus a very large number will produce a very large number. So this will end up being infinity. Now, in this case, it's important to think about whether I'm plugging in 0 in the limit from the right or from the left. Because my interval is from 0 to 4, it means that I am plugging in to the right of 0, which means that this is a very, very small positive number, which will mean that this is indeed a very, very large negative number. So I am going to end up with negative infinity here. So now I need to compare these two numbers, infinity of course not being a number, but a value larger or smaller than any number that you can think of. So between the two of them, the larger number is 3.75, so this will be my global maximum. But because negative infinity is not an actual number, this means that in this case, I have no global minimum for this function on this particular interval. I strongly recommend you pull up your graphing calculator such as Desmos and actually draw this function and then think about what it looks like on the window from 2 to 4 and on the window from 0 to 4 to see if you can replicate these results on the graph and persuade yourself that this is indeed the global max and min of the function on this interval and the global max and no global min for the function on this interval.
So let's take a look at a problem here. We are given this function that describes the probability of a cell dividing. And we're asked, between times 0 and 10, when is cell likeliest to divide and when is it least likely to divide? So what we're actually asked to find here is global max and global min of this function. Again, that means all we have to check are critical points and endpoints. The endpoints in this case are given to us, 0 and 10. Critical points we still have to find, okay? So in order to find critical points, remember we have to take a derivative, see where it's equal to 0, and see where it does not exist. So the derivative here turns out to be minus 2t cubed minus 8 all over t cubed plus 16 squared. I'm looking for where this is 0. And again, it's one nice compact fraction, which means that it's 0 when the top is 0, which in this case then turns out to be t equals 2. And I'm looking for when the derivative does not exist. Because it's one fraction, this happens when the bottom is 0. And in this case, that is when t is equal to cube root of minus 16. Notice that we can't take cube roots of negative numbers. However, the one thing that disqualifies this root from consideration is the fact that I am only interested on the interval from 0 to 10. And this is most definitely not in the interval. So this not on the interval from 0 to 10, not in the interval from 0 to 10. Okay, so these are my two critical points, but I am only going to take the one that actually belongs to the interval of interest. Excellent. My endpoints are 0 and 10. So all together, I have 3 points that I'm going to plug back into the function and physically discover which one of them yields the highest and the lowest y value. Okay, so all I'm going to do now is actually evaluate my function at 2, at 0, and at 10. That's how powerful the extreme value theorem is. It says if a global max and min occurs, or when it occurs only at critical points or endpoints, which means that I already have all the points I might need. Now I just have to figure out which one is the highest and which one is the lowest. So I'm going to plug all of these back into the function itself, not into the derivative, but into the function. And now all I'm doing is looking at these numbers. Which one's the smallest? 0 is the smallest, which means that this guy is the global min. Which one of these three numbers is the largest? 0.083 is the largest, which means that this one is the global max. Okay, so once again, for global extrema, you don't need to analyze the behavior of the function itself. All you need to do is find critical points, endpoints, and plug all of them back into the function itself.
Please note that you have an empty slide with an additional problem in the lecture notes, as well as this handout with extra problems to fill out and try out for yourself. This is a bit more high level. You are not provided with the actual formulas for any of these functions, but rather are supposed to draw on your understanding of the graphical information and the results that connect the graph of the function, its derivative, and its second derivative. So give it a go and ask me any questions you might have about it in office hours or over email.